Oh. Thank you.
Big phone's censoring what we're doing. They just don't want people to know. What is the relationship between S and theta?
ds equals r d theta.
Say it again.
ds equals r d theta.
Taking it the step right before that, S equals R theta, so ds is equal to R d theta. And so I have K lambda over R squared, integral of R d theta, sine theta. R comes out, will cancel out, and so I'm left with K lambda over R times the integral of sine theta d theta. I now have the single variable, we get the limits of integration. The smallest value for theta is 0, and the largest is pi over 2. And so this becomes K lambda over R cosine theta from pi over 2 to 0. And there is a small mistake. We can correct it at this point, but so K lambda over R times 0 minus 1, or negative K lambda over R. That is the, I feel like we,
Isn't it negative cosine?
where did that negative come from? When you plug pi over 2 in for theta, you get 0, plug 0 in for theta, you get 1, so it's 0 minus 1.
Yeah, but
The integral of sine theta is negative cosine.
That's it.
Okay.
I thought something got off there, so this is negative here, negative, positive. Here's the mistake. We thought through the direction. I know that the electric field, the I hat component of the electric field is to the left. I did not put that in here, so there actually should have been an extra minus sign right here, which means there's one here, one here, one here, one here. Makes that positive, that's positive, and that becomes negative. Thank you. Or we have the magnitude over there. I know it's going to be to the left. So our final electric field, given this situation right here, given I hat, J hat defined like that, is, probably don't want to, actually we have numbers, so we could actually solve for lambda. So K lambda over R negative I hat plus K lambda over R J hat.
How would we find radius again? Or, oh wait.
How do you find, yeah, radius right there?
Will you give us that relationship on the test?
That 2 pi r is the circumference?
Yeah,
Just
just to be safe.
We have trust
You
issues.
should give us, the integral of sine equals negative cosine, just so we don't get like a minus sign mixed up in there. It always happens.
Trust issues.
It always happens.
why spoil the fun of having a minus sign in the wrong spot? I will probably forget because the first page is already done, but just ask.
Okay, no worries.
Okay. Yeah, my long pause was I was trying to figure out what happened to the minus sign because I knew that this should have ended up being positive the way I had done it. Because I left the minus sign out at the beginning. That was decades ago. I'm supposed to remember how to do that? All right, other questions?
Can I ask one more? Sorry.
Sorry, was your question answered?
Yes,
Okay.
absolutely.
It's this one. Number 10.
Two infinitely long conducting wires lie side by side in the XY plane, center separated by a gap of 0.5 millimeters. Wires have radius, yada, yada, yada. All right, so part A is about the electric field in between. And then potential difference. And.
So this is not there for our exam.
Right, the capacitance per unit length would. Yeah, I think that would show up in the next test. Was that the only question, or do you want me
No,
to?
it's just.
Okay. All right, so. So I have one along the x-axis, 0.2 nanocoulombs per meter, and then one at 0.5 million. Okay. Let's see how much of that I remember. There's my x-axis. This has linear charge density of 2 nanocoulombs per meter, I believe. And then there's one here, which is, there's a distance here of is it 5 millimeters?
Yes.
0.005 meters. The thickness of the wires is 0.001 meters. And this has a charge of -2 nanocoulombs per meter.
Oh, so they're not side by side like this.
No, I said the infinitely long, right?
Yes.
Yeah, no, they're.
Oh, yeah, that's true. Okay.
Side by side like that. Does that clear everything up, or do you want to keep going?
Just keep going.
Okay. So I'm asking, what is the electric field in between here? So if this is x is equal to 0, oh, the other one's that. What was the orientation?
The wire which runs along x equals 0.5 is the negative.
All right. So that's my x-axis right there.
Oh, it's actually 0.2, negative 0.2 nanocoulomb.
A point. All right, so I'm trying to find the electric field in between. Yeah. So positive x runs in that direction. So I know that if I have a point right here, the electric field always goes towards the negative, away from positive. So I have an electric field coming from the positive in that direction and from the negative in that direction. Let's let that be my I-hat direction. And by the way, as these things get more and more complicated, if you can't picture what I'm writing out, generally I don't do pictures just because they're so hard for me to draw using a computer. So if you're not picturing it, just ask and I can draw it up on the board. Despite the brilliance of prose.
What was the test?
Sorry.
I know that the electric field coming from an infinite line is equal to, I think it's 1/2 pi epsilon sub naught lambda over r. I think that's right.
Yeah.
I know it close enough so that I can look on the first page and I can find it, or I can just derive it. So from the negative charge here, so the electric field at this point, P, would be the electric field from the positive charge plus the electric field from the negative charge. Positive charge I know is going in my I-hat direction as a defined I-hat, because it's going away from the positive one. So this would be 0.2 times 10 to the negative 9th over 2 pi times 8.85 times 10 to the negative 12th times r, which is some distance right there, which we'll call x. And that will be in the I-hat direction. From here, so So that distance there is x. This distance here would be 0.005 minus x. So from the negative charge, I'm not worried about the negative sign because that's telling me a direction and I already know the direction. So 0.2 times 10 to the negative 9th over 2 pi times 8.85 times 10 to the negative 12th. And then the distance is 0.005 minus x. I hat. Use a calculator, come up with numbers. We have something over x plus something over 0.005 minus x. We can get a common denominator, whatever form that you're supposed to express the answer in. The second part, the potential, because we have some function of x here, and I said, what's the potential between the two? I know that the potential difference is going to be negative integral E dot. Did I say from the positive to the negative or negative, positive to negative?
Positive.
So I'm looking for the electric potential going in that direction. What can you tell me about my answer to my potential difference from going from here to here?
Oppositely signed. Oppositely signed.
No, just decreases.
Negative.
It's gonna be negative.
Negative, this is what you meant by oppositely signed. But it better be a negative in the end. Because I'm going from a high to positive to negative, it's from a high potential to a low potential. And so this is what we're doing. So you'll have a formula for E right here from part A, and then you just do a little integral. And it looks like there's some natural logs involved.
So we're supposed to be simplifying that formula up there and then plugging it into the bottom one?
Yeah, well, the answer to part A was this,
Okay.
and then you'll use that in part B. Yeah, so this is just some number abbreviating it. So this is just gonna be, we're gonna call this A over X plus B over 0.005 minus X I hat. And so when I do my integral here, dx here is basically I hat dx, because I'm going in the I hat direction. And so the I hat's gonna go away, my dot product, and so what I'll end up with is the negative a natural log of x from 0.001 to 0.004, that's in the problem, those numbers, plus negative natural log, negative b natural log of 0.005 minus x from 0.001 to. If you go through all that and end up with a positive answer in the end, then it's a matter of going through and trying to figure out, all right, so where's my mistake? Or slap a negative sign on it at the end, which is not preferred, but sometimes that's what you do. So, this, okay. Any other questions on this one? All right. Take care of that last one. Any questions on this one? Any other questions?
We take 5.
Sounds good. Take 5, come back, we'll talk about current, resistivity, neat jump like that. I'm just gonna let it run, just so I don't forget, and, so if you need to talk to me about something private, probably in front of the camera is not the time to do it.
Did you ask me something?
No, just what Tesla does.
Oh, that was spring 2015, number 10.
We last left off exploring current density, but now let's take a look at some of the same variables we used before. Free charge density, I might have called it charge particle density before. Basically, it's the number of free charges that can flow per unit volume. It is material dependent. Copper's got a lot more of them than So, trying to think of something that's horrible at conducting. Oh, well, any of the noble passes. Were you asking a question?
Is it still chapter 28?
Chapter. Sure. Yes, chapter 28. Trevor, just making sure you got on film for the alibi. If anyone else needs an alibi, you can just walk away by right now. All right, so we have some high potential over here, some low potential over there. If you need more of a visual, I've got basically a wire hooked up to a battery. I have the high side over here. This is my plus side, and then the negative side over on that side. So my high potential is on basically on the left, and the low potential is on the right. The electric field will be traveling from the plus side to the minus side, and it basically channels along the wire. Since we can get far more sophisticated in theory, and we'll come out with the same place, come out in the same place. But do I have an electric field that's basically traveling in the direction of what we'll consider current flow? As we discussed before, the current is flowing in one direction, thank you, Ben Franklin, but the electrons, in terms of particle movement, are going in the other direction. And electrons don't really travel in a straight path, unless you want to get into superconductivity, which we are not. So the electron, as it travels through the wire, is going to hit something, and then bounce, and hit something, and bounce, and then. So the electron is going to be bouncing all over the place as it moves, and even though the electron might have a particular speed, there's a sort of overall average speed known as the drift speed. So let's take a look at the current. I know current is the charge per time that flows past a particular spot. I'm going to sort of drop the delta. The delta is indicating that it's the amount of charge that passes by, and I'm just going to use Q as the amount of charge that's passing by. So I have Q over time.
So that I means current flow?
Yes, I means current.
Just current or current flow? Is there a difference?
Current, I would not distinguish between the two.
Okay.
There is current flowing. I guess by definition, current is flowing. So I was just being redundant then. Now the amount of charge is going to be equal to the number of free charges times the charge. So that's going to be whatever the charge of what's moving, and it's going to ultimately be the electron, times the number of free charges over time. And I know that the number of charges is just going to be the free charge density times the volume over time. And my volume, well, if I take a specific section right here, I have some cross-sectional area times this distance right here, which I'll just label as delta x. So this becomes Q in A delta x over time. This delta x over time, that's just the drift speed. So this becomes Q, the charge of whatever's flowing, times the charge carrier density, times the cross-sectional area of the wire, times the drift speed. And now it's quite obvious. Let's drill down a little bit more. So the drift speed let's let's just work in a constant acceleration sort of frame of mind, that drift speed on average is equal to the initial speed on average plus acceleration times time. Average time. Because the acceleration, for the most part, except when it hits things, when it's been between hitting things, the acceleration's constant, because my electric field is constant. You know, I got a battery in it, I guess it could be draining, but we'll assume a constant power supply. My electric field is relatively constant, so the force on the charge is going to be relatively constant, except when it hits things. So I'm looking at the times in between hitting things. On average, my initial velocity is 0. It's going to hit something and bounce off, but it's just as likely to hit something here and bounce off as it hit from the other side and bounce off. So on average, my initial velocity is 0. So my average drift speed just becomes acceleration times this average time. Oops. And so I'm going to let my average time be symbolized by a tau. My acceleration is force divided by mass. And the force being applied to my charge is just the force from the electric field. So this will be Q times my electric field over the mass of the charge. So plugging that into here, try that one again, into here. We end up with my current is just Q, lowercase n A, times Q times my electric field over M times tau. I have gotten rid of the vectors. That's basically the magnitude of the electric field. We assume the electric field is running anti-parallel to the charge flow, the negative charge flow. And let's go ahead and talk about the 99% case of it's electrons. That's the charge of an electron. Oops. Magnitude of the charge is just the magnitude of an electron. So I have N A E squared times capital E over M times tau. Make sure I didn't move something out. I'm going to write this, that's a tau. I'm going to write this slightly differently. I'll make sure I pull the right stuff out. I want to pull A and E out. So I'll pull the A out and the E out. And I want the N E squared tau over M. And that would be the mass of the electron at this point. All right. This bit right here that I stuck in parentheses. Lowercase n is the amount of free charge per volume for that material. It is a material specific number. E is the charge of an electron. That is relatively constant. Tau is the average amount of time between a charge, the electron hitting one atom and then hitting the next atom. That is material specific because it depends on how closely packed those atoms are. Mass of the electron, close enough to constant. In other words, this has two constants in it and two things that are material specific. So we can just consider this whole thing to be a material specific value or quantity, material specific quantity. And that is sigma yet again. This is known as conductivity. And yes, they could have pulled the E squared over M out, but they didn't. So it's bundled into this thing called conductivity.
So that whole formula is equal to the sigma conductivity?
Yeah, the
The.
any squared tau over mass. So my current is just equal to my conductivity times the area times the magnitude of my electric field. If I divide by area, this is more of a side note, I get I over A is sigma E. What is I divided by A? See what you remember from a week ago?
Step 47.
Pardon?
Step 47.
Current density.
Current density. Still didn't quite hear what you said.
I was just asking what chapter that was from, so I
Oh.
can look at the flashcard.
Chapter 28, it's chapter
Okay.
28. And so we have current density is equal to sigma times E, what I sometimes think of as the Joule equation. And I'm probably the only one who thinks of it that way, but. But we have this equation here, which is not as useful as we would like. So remember that this electric field is being produced by the potential difference in the battery. Because I have charge flowing here, there is a potential difference from here to here. There's some potential difference. Or we can expand it to include more if we need to.
I'm sorry, so J is current density, right?
Pardon?
J is current density?
Yes.
Okay.
Yes.
Just making sure.
Anything else before I just rattle on? Since I'm treating my electric field as relatively constant, that's just equal to sigma A delta V over, I guess, delta X. Or we can expand it. I mean, it doesn't necessarily have to be limited to that. This ratio here is relatively constant. Since I'm considering my electric field constant throughout the wire, this just could be sigma A. So this, let me just write it, SEG for segment. This is the potential for the segment that's that long. Or I could just put it delta V for the whole thing divided by the length of the wire. Rearranging this, if I solve for delta V, because don't forget, this is equal to I, my current. So I multiply both sides by L, divide by A and sigma, I get my voltage